All right, we're back. We're going to be talking about page 2 of Notes 25, volumes by shells, cylindrical shells, which should really say tree rings because you just make little tree rings and that's how you accumulate your volume. So we came up with this formula, and what I wanted to do is I just wanted to point out that this formula can easily be thought of as volume equals 2 pi, and then the integral from a to b of the radius times the height, and then dx. So that's another way to think. That's actually how I think of it. I always think like, what's the radius? What's the height? Now let's do this integral. So I always go through that process. Things can be a little more complicated if you're not going strictly around the y-axis, or basically it's like, where is the region, right? So because we're thinking of the radius needs to be positive. This is not the same as when you're doing volumes by discs and washers, the other method, where you're just going to square your radius, so it doesn't make a difference. Here it makes a difference because you're not squaring, right? You're just doing radius times height. So if the axis is to the right of the region, then to get a positive radius, we're going to have to do, so you can like draw a little representative sliver here, and then the radius that you're getting is from here to here, right? And so all the possible values for where this thing can be are between a and b. That's why our bounds are a to b. The radius has to be the right-hand thing minus the left-hand thing. So it has to be, this is just some x value between a and b. It has to be the axis minus x. So that's why in this, when the axis is to the right, you're going to get 2 pi, the integral from a to b, axis minus x, that's just the radius, times f of x, which is just the height, and then dx. Okay, so that's if it's to the right. Always just draw it and like draw your little representative slice, put in the radius. You kind of can't get it wrong if you do that, or at least I don't recommend you get it wrong. I mean, who would ever recommend you get it wrong? Here your axis is to the left of the region, so let's draw a little slice. And this is going to be at some x value. That x value is somewhere between a and b, which is why our bounds are from a to b. And then our radius is here. This is our radius. And you have to do right take away left. So when you do right take away left, it's x minus the axis, which is where this is coming from. And again, radius, height. So it could be a little more complicated if the x-axis isn't the like base, right? We could have a second function, maybe g of x, and then the height will always just be f of x minus g of x, or more generally, I don't know why I said will always be f of x minus g of x. No, generally it'll be top take away bottom. It doesn't matter which is on top. The top curve minus the bottom curve gives you the height of your cylindrical shell. The radius, you just look at it. Where is the sliver? Is it to the right or is it to the left of the axis? Do the thing that makes sense. So let's see if we can do some problems. But I do want to point out, so I'm a firm believer in like use the best method for whatever you're doing. This method is super good at going around vertical lines. It's super annoying to go around horizontal lines with this method. Just like the other method, disc and washers, really set up to go around horizontal lines. To go around a vertical line, you have to like solve everything for the other variable, then you have to like really check the bounds you were going to use. It's like that method can be used that way, but it's probably not meant for it. It's almost like the two methods kind of are meant for different things. And so if you're using shells, I pretty much will only use shells for vertical axis of revolution. So if you're going around a vertical line, and I always use discs and washers for horizontal, unless someone tells me I have to do it another way, or it's possible to run into difficulty where you like have to use one or the other. Not have to, but it would be very preferable. So let's do an example and see how it goes. So on the volume of the solid obtained by rotating the region under the graph, blah, over the interval from 0 to 1 about the y-axis. All right, so I'm going to try to draw this. It does not need to be accurate. So let's go here. We're going from 0 to 1. So I mean, I guess if I plug in 1, I get 1 minus 2 is -1, plus 3 is 2, minus 2 is 0. So actually, then the y-intercept is definitely 1. Let's say that it looks not like that, but whatever, close enough, right? So this is f of x. We're going around this. Okay, draw yourself a little sliver. And then this x coordinate right here is any number between 0 and 1. So I know that I'm setting up 2 pi, the integral from 0 to 1, because that's where x is. It's between 0 and 1. Now, what's the radius going to be? Well, this is my radius. Okay, why am I cramming things? I don't really expect an answer, but like, why am I doing that? That's our radius. So x is to the right. Our sliver is to the right of the axis, so it should be x minus the axis. The axis is x equals 0, so this is just going to be x. And then the height of this thing is going to be, maybe remember that you have colors available. The height is just going to be whatever f of x is. So we're going to multiply by f of x, and then dx. And then this says not to use a calculator, and that's really unfortunate. So 2 pi 0 to 1 x 1 minus 2. This is going to be terrible. 3x squared minus 2x cubed. All right, so we expand. 0 to 1, it's going to be x minus 2x squared, 3x cubed. It's going to be sad if I get this wrong. I'm going to be sad if I get this wrong. I still have to integrate. So, oh my gosh, what happened there? Auto whatever's dx. It's like, what would that auto shape even have been? Like, who knows? So 2 pi. All right, integrate 1/2 x squared minus 2. At least we only have to plug in 1, I guess. I mean, still not great. But, I mean, we have to plug in 1 and 0, but when you plug in 0, it's going to 0 out. So this is going to be 2 pi 1/2 minus 2/3 plus 3/4 minus 2/5. What is the common denominator here? Like 60? 2 times 3 times 2 times 5. 2 times 3 times 2 times 5. I think it's 60. I'm going to go with that. 2 pi. So it's 30 minus 40 plus 45 minus 24 over 60. Which is, I have a lot of room on the side that I did not realize that I had. I'm going to move this. Okay, and then we went up. Oh, nope. And we went up and over. So this is 30 minus 40 is negative 10, plus 45 is 35, minus 24 is 11, times 2 is 22 pi over 60, or 11 pi over 30. Should we check that? I think we should check that. Let's do that. So I'm going to switch to the calculator and hopefully confirm my answer. So I'm going to define f of x, just because I don't want to type it more than once if I had to do multiple things with this, which I actually already know that I don't. Oh wait, no, I do. In the next problems, I have to use this again. So this is going to pay off. This is like an investment. All right, 1 minus 2x plus 3x. Okay, so we want 2 pi times the integral from 0 to 1 of x times f of x dx. 11 pi over 30. Yeah, it never doesn't feel good when you get it right after doing all of that. Like I've done a lot of these and I still lack the confidence to be like, no, nailed it. Don't care what anyone says. All right, you know what I'm gonna do? I'm gonna stop this here, come back in the next video, do the rest of these problems, and maybe potentially finish the notes, potentially. We'll see. But anyway, all right, so I will see you in the next video. So I hope you found this helpful.